Hello, good morning everyone. I think we are ready to start. If somebody joins in the meantime, no problem. This is the course Processing Sentinel Data in the Cloud with Jupyter and Sentinel Hub APIs. My name is Andrzej Zlinski. I am the communication person for Copernicus Data Space Ecosystem. And my colleague William Ray from Synergize unfortunately couldn't join us today, so I'll try and stand in for him. Let me show you the agenda. So we start with a brief introduction to Copernicus Data Space Ecosystem. We will look into Copernicus browser, how to visualize satellite imagery. We will set up the Jupyter lab. We will take the first step with Sentinel Hub APIs. At 10:30, we have a coffee break. And then in the rest of the morning, we will do some more advanced things, statistical analysis, looking at data visualization, multi-temporal data. And then in the end, we will have a Q&A. Now, since there's not too many people in the group, I think we can be absolutely interactive. So if you have a question or you get stuck or you don't understand something, just stop, raise your hand. I will try and come up and help you or answer your question. Probably if something is not clear to you, then it's not clear to 5 other people as well who just don't have the courage to step up. So please go ahead and interrupt and ask questions if something is the matter. Once more, before we start, please register in Copernicus Data Space Ecosystem. Let me show you once more how. So on the CDSC main page, dataspace.copernicus.eu, and under this login button, if it doesn't show register for you automatically, then you go to your profile, and then here you have a register button if you're not logged in yet. It's a very simple registration process. We're not asking you to donate your blood. You simply fill in your name, your affiliation, some very, very basic details. This is just for the sake of keeping track of data usage. So you're not sharing your code. You're not handing over any rights to us. This is an open system. So the rules are very, very simple. So let me introduce you quickly to CDSE, as we call it, Copernicus Data Space Ecosystem. So in the typical satellite data processing pipeline, you start with a satellite where the data is, of course, downlinked to Earth. It's stored on a server where it's pre-processed. It's brought to some sort of format. The initial corrections are done on the data. And then you want to create a processing operation. In this very simple case, this is a thermal visualization of Stromboli volcano in the Mediterranean. So what you see is whenever there's an eruption, the radiative power of the lava and ashes is providing a yellow or red signal. But to reach to this level of data processing, of course, there's many, many steps you have to go through. You have to put the data in a common coordinate system. You have to cut them out for your area of interest. You want to filter away the cloudy pixels. Then you select the bands that you are using for this visualization, the red, green, blue, and the shortwave infrared bands. You apply some sort of mathematical calculation. And then the end result you put into a specific file format. You assign some time to every step. So this is a typical processing operation. And then your next move probably is to create some sort of visualized output, like a graph, and then to show this on your computer. And in Copernicus Data Space Ecosystem, the sort of paradigm shift is that all of this is happening on the remote machine. So your computer is just, come on in, it's just a visual interface to the end product of the data. The data access, the processing itself, including the query, the visualization, even the rendering of the graphics, is happening on the cloud, and then the final product is sent to your computer. Why does this make a difference? It makes a difference because you don't have to have a big computer. So again, I remember the days when I was a PhD student, and when I got my first research project, the first thing I bought myself was a gamer laptop, right? Very expensive, very big laptop, because I told my supervisor, I need to process a lot of data. I need to have this powerful computer. And I was right. But now, with everything in the cloud, you don't really need to have a powerful computer to steer it. You don't need to have a big data storage where you download the intermediate product. It's all in the cloud. You can tell the machine exactly what you want, not just the area of interest, not just the bands, but the actual product, even the visualization, and then that will be sent to your computer. So we hope that this makes remote sensing accessible to a lot more people. If the computer is not the limitation, then the next limitation is that it's difficult. Now, we've set up this system with the APIs where we are really, really trying to make it easy, and I hope that in 2 hours you will be absolutely convinced that this is super easy. So we are trying to set up a system of components which really, really lowers the bar to remote sensing, to allow non-specialists to work with it. So Copernicus Data Space Ecosystem is the follow-up of the Copernicus Open Science Hub, which used to be the data distribution platform for the Sentinel satellite data. So at the core of everything, of course, we have the Sentinel data. This means, in our case, Sentinel 1, 2, 3, and Sentinel 5P, and some data for Sentinel 6. All the data is instantly available. Again, if you remember Copernicus Open Science Hub, for the last 2 years, the data was instantly there. If you wanted anything before that, you had to submit a request, you had to wait for it to be copied from the tape archive, and then sent to you when the request was prepared. Now everything is instantly available. And then we have Copernicus Contributing Missions data. Copernicus Contributing Missions are market-based satellite operators who have a data sharing agreement with the European Space Agency. So for certain purposes, they have created data mosaics, data products that you can access in the data space depending on the usage conditions. And this means that high-resolution mosaics are available to certain users. And also now, a new generation, actually, of new space actors, including thermal imaging, hyperspectral imaging, high-resolution regular data, are sharing some new data sets which will also be available in the data space. And then we have additional Earth observation data. The most important one is the Copernicus elevation models. So Copernicus DEMS are available globally inside CDSE. And now you can access the data with APIs. An API, you'll hear this word a lot. An API is an application programming interface. It's essentially a machine-to-machine interface that allows the code you build to communicate with the code on our server. So you can actually create a request, and you can access the data on our storage just in the same way as you can access the variables that you define in your code. This is what the API is for. We have several APIs because APIs are like languages, English, French, German. We have Sentinel Hub, we have OpenEO, we have OData, we have Stack, depending on what people have learned already or what they prefer to use. So we have a lot of APIs. And connecting the APIs with the data, we have the Copernicus browser, which is going to be the first tool which we play with. This is an online web browser-based system for looking at satellite images and doing small analysis tasks. And then again, I've talked about the problem of learning. Learning Earth observation coding is not easy. You guys all know. There's so many things you have to learn or understand at the same time. And we are trying to make this easier. And there's 2 ways to do this. One is to reduce the code to the bare minimum. And if we have these APIs, then the API takes care of the visualization. You don't have to build a front end to look at satellite data. And the API also takes care of the back end, the whole thing of accessing a data file, putting it in the right format, putting it in the right grid. This is done by the back end silently. And then your coding can concentrate on the very analysis pipeline that you're building. This is what we are doing to make this easier. And the other thing we are doing to make this easier is to provide a lot of example code to help people get started, really, really from the very basics all the way to advanced operational ready data pipelines. And then again, we have cloud computing capacity. Essentially, ESA is handing out virtual machines for free for everyone. So in order to work with a lot of data, you have to have big capacity. And apparently, it's easier to do this on the same machines which are storing the data. So you're not actually bringing the data to the machine. You're just bringing the code to the storage. And then the very same physical infrastructure in Warsaw and Frankfurt, which is storing the data, is actually the one that is running your analysis code. And then the whole thing is very close to the data. It's really, really fast. It's difficult to match this performance with an external virtual machine provider. And so this connects in the Jupyter lab and in our online code labs, where you're actually running your code on the virtual machines that host the data. You have the code base to work with, and you have the cloud computing capacity backing this up. And for public agencies, for government institutions in the EU, this cloud computing capacity is also available at larger quotas than what individual users get. This is called the Copernicus Service Level User Program. So it's possible to apply for a large quota if you are a public institution or if you are doing something related to Copernicus services. And then we have a user identity service. We hope to federate with additional data spaces. So the dream is to have one unified login, the Copernicus Data Space Ecosystem login, which allows you to connect to many different sources of data that you can then bring together in your code. And we also have a little traceability API. This allows people to check the origin of a satellite image product, because there's a checksum inside every product, and then as it goes through the processing stages, this checksum is kept. And if there's some sort of AI tampering with the data or manipulation or some illicit changes, then of course this checksum will be affected, and this API can check, it can trace it back to the original source to verify that this is the original product of the data. This is important for legal cases, this is important for defense cases, the API is there. And we hope to build out of all this an open ecosystem in the industry ecosystem sense, which means that we are open to partners joining Copernicus Data Space Ecosystem as registered third-party services or registered data services. And this will all grow the Earth observation market, both for startups and for large companies and for government agencies. Okay? Any questions to this? Good, let's see some data, right? So first of all, we want to get started with Copernicus browser. We want to look into visualizing satellite imagery and see what the first things are that you can do online. Anyone have a guess on what this place is that I've shown on the satellite image? Is it familiar to someone? Okay, it's Heard Island in the southern Indian Ocean, close to Australia. So what you want is browser.dataspace.copernicus.eu. So open a web browser of your choice. Type in this URL. It also works on a phone, yes. Browser.dataspace.copernicus.eu. So Copernicus browser is a completely free tool. It works on any platform, a tablet, a phone, a computer, a big computer. And this allows you to access all the free and open imagery that we have, and also some of the environmental data that is also part of Copernicus Data Space Ecosystem. It's available in, I think, 10 different languages at the moment, and we are still open to people who want to contribute translations in other languages that we don't have yet. And in addition to looking at data, it also supports some kinds of quantitative analysis. It allows you to download data products at various resolutions and formats, and you can start developing algorithms in there. And one of the nice tools that I will show you is for sharing links. So if you have a satellite image that's interesting, you can generate a short URL and share it with anybody. And if they click on that, it will open up in Copernicus browser and people can browse in and pan around. So this is used actually a lot for fact checking. Everybody successfully opened Copernicus browser? Yes? Okay. So this is what you see, right? In the top right, for you guys, I don't know why we have Zermatt here. If you just type in Riga, you will see a satellite image of Riga. The system will navigate to Riga, and then on the big green button, you click Show Latest Date, and that will pull up the latest satellite image. Let me also do this on my side. Okay, Copernicus browser, so far nothing is loaded, but if we go to Riga, here we are, and I click Show Latest Date, then this is what we see. Quite cloudy, but otherwise nice. If you're on a small screen, a smartphone or something, you can click this sidebar away, and then it's not going to be in the way of looking at your satellite data. Right, so what do we have here? You can choose the language with this little drop-down menu. I'm staying with English for now. You can change the background with this little layer menu. So there's two different backgrounds. One is OpenStreetMap. The other is the Sentinel-2 mosaic, the latest Sentinel-2 mosaic of the last 3 months. So one of the data products we have here is a quarterly cloudless mosaic, and you can just use that as a base map if you want to compare with changes. With this little button, I can show and hide the satellite image layer that I'm working with. And then you can also add some overlays, labels. The labels are, again, from OpenStreetMap, country borders. Clouds?
They are clouds?
Yes.
Clouds.
Yes, these are clouds. If we change to a different date, we can try and find an image which is less cloudy. So if I just open the calendar panel here, you will see some dates have a gray image. Those are the cloudy ones. Some of them have an image framed in blue. Those are the ones that are less cloudy. And what do we take as cloudy? We have this threshold for cloud coverage. If I increase the limit, then I'm getting more images, which I am considering cloud-free. If I reduce it, then I only have one, right? So let's go with 20%, and then maybe this image on the 8th of September should be quite cloud-free, right? So this is a pretty image. What can we do here? We can create an area of interest. So if you just click a rectangle like this, then you have created an area of interest. This is going to be a small area where you can query the properties of the data. And then if you click on this little graph here, you are looking at the spectral explorer. So you know that Sentinel-2 has these 13 spectral bands. And here you see a graph of the reflectance value in each of the bands, right? You can see the spectrum of the area that you are interested in, of the little rectangle that you have clicked. And we have some reference spectra here. So you can compare with the spectrum for water, for grass, for soil, for concrete, for snow. So our little place I've just selected is somewhere between soil and grass, right? So it's probably, yes?
Does SAR observations go through clouds?
It goes through clouds. I can show you how to look at SAR observations as well. If you just change the data source, instead of Sentinel-2, you can select Sentinel-1. You look at show latest date again. This is what you see. Now this is not obscured by clouds. So this is the 28th of September. It's not affected by clouds. It's a bit more difficult to interpret. It's not quite trivial how these properties are generated. But it's possible to look at the basic land cover. You can also see some vegetation properties, and you can observe change. But right now, for the sake of the example, I'm going back to Sentinel-2. So again, here's our area of interest. And I'm changing to a different data product. This is now, yes. This is now the near-infrared false color image. We have a slight glitch at the moment in Copernicus browser because we have just changed the backend to a different API. So for those of you who are following Copernicus data space ecosystem more closely, the two big API families are Sentinel Hub and OpenEO. And now OpenEO is powering the browser, but some of the visualization scripts tend to have a problem. So if nothing displays, you open this little code icon, and then from OpenEO process graph, you switch to custom script, and then it's going to display. We are already aware of this issue, and my colleagues are working to correct it. So what you see now is a near-infrared false color image. So we are working with band 8, band 3, and band 4. And so red is vigorously growing vegetation with a high chlorophyll content. I can show you on the Spectral Explorer as well. So this here is band 8. This is where vegetation has the reflectance maximum. So if you're interested in vegetation, you're probably using this band. Now let me go back and choose a different layer, NDVI. NDVI is a very popular vegetation index. It's just comparing the red and the near-infrared band. Again, I can show you in the Spectral Explorer. So NDVI compares this with this, right? So this step is going to be really large if you have vegetation. It's small if you don't have vegetation. So what you can do here, you have an area of interest, and you can look at the time series for that area of interest. If you're not looking at an RGB visualization, but a single parameter, which is the output of a spectral index, then you can look at this time series. So now what's happening in the background is that the API is querying all the satellite images for the last 1 year. It's calculating the NDVI for the area of interest, and it's calculating the mean and the standard deviation and adding it to this graph. This is what you can do very quickly. Yes?
Does they transform to some cartographic projection? Some from the imagery.
This is done in Web Mercator. You can create an output in various cartographic projections. I will show you how in a moment. So now we have a time series. It's a noisy time series, but we can remove the clouds. Again, now I am in the API request. I am creating a limit. I am only looking at the data which have less than 24% cloud cover. And then you see how the time series sort of gets smoother. And you can export this as a CSV. So again, if you just want to do very quick analysis, if you just want a couple of numbers or a graph, the easiest thing is to do it here in the browser. Now, let's move over to the download panel. I'm closing the area of interest for a moment. So here, you have 3 different versions. Basic download is something like 900 by 600 pixels. So it's just a very small image for sharing on social media or embedding in a document or something. You can add the OpenStreetMap background. You can show a legend. If it's available for your spectral index, you can crop it to your area of interest. Now, in the analytical download, this is where you're actually downloading a file that you can use in your GIS. So this is again, you can set the pixels. Even you can create a custom pixel size if you want. You can go with TIFF or KMZ or 32-bit float TIFFs, again, depending on what you want to analyze. You can change between the visualized product or the individual bands. And this is where you can select between a couple of projections, not too many, but a couple. And then later on, you can reproject it in your GIS if you need to. And finally, we have high-resolution print. This is for creating print quality products, so you can set the DPI here. The default is 300 DPI, and you can create very big products with tens of thousands of pixels with print quality. Typically, for the API requests, the limit is 2,500 by 2,500 pixels. If you're doing a print quality download, then it's actually stitching together the image from multiple API requests. Then you don't really have a limit, but it can take maybe an hour to download a very big image. What else do we have here? The scene classification map is a product of the classification that's generated during the atmospheric correction. So it has some basic classes: cloud, vegetation, bare soil, and so on. And finally, I think let me wait for this to load. Yeah, we've done this. We've done this. I haven't shown you the histogram. Let's go back to NDVI for a second. So, yes? I think it's probably the network, actually, because we're all on the same Wi-Fi. It should be actually faster than usual, because a couple of days ago a new version was deployed, which should be about 60% faster. So I don't think it's in the system. It's probably the network speed. So once more, let me look at an area of interest. I'm checking this wetland. And then with the histogram tool, you are generating a histogram of the spectral index values inside the area. So again, you can check whether it's a unimodal distribution, it has one peak or several peaks. You can understand the changes if you move through time. So if we select a different date, we go back to March. And then we look at the histogram again. Then we will see how it's different. The NDVI value peak is much lower. I'm going back to true color just to create a time lapse. If we move over to the Riga harbor, and you click this little film icon, then you are creating a time-lapse animation. Again, in the background, this is an API request querying all the images from the area that you have on screen, creating an image product of each of them, and ordering them into a sequence. Right now, we are looking into a very short time period, but I can extend that from the 1st of January to the end of September. I want 1 image per week. And then, as these images are loaded to the time-lapse, we can select the ones we want to exclude if some of them are cloudy. And then we can create a small animation. There's one more thing the time-lapse helps you with. We have a credit system. So the processing units that you consume are taken from your credit. You have 10,000 processing units per month as a regular user. What's wrong here? Yes, here we go. OK, I know what I did wrong. We still have the area of interest. I have to remove that. Yes, so 1 processing unit has the equivalent of one image in the time-lapse, because 1 processing unit is 512 by 512 pixels and 3 band output, RGB. So this is the amount of volume, processing volume that you have for a month. You can create a time-lapse of 10,000 pixels, or you can create a process which consumes, no, not 10,000 pixels, 10,000 images. Or you can create a process that consumes this amount of units. As a comparison, what we like to say, my company is based in Austria, so you can create an RGB mosaic of the full area of Austria every month using, from all the images that arrive in that month from this amount of processing units. So it is actually sufficient to do national scale processing. So right now, we have a cloud coverage limit of 23%. Maybe we scale this a little bit up. And then we get 10 images, and we can play them in a time lapse. So you see a little bit of movement, ships coming in and going out, clouds moving around. And then once the data is there, it's also possible to download this as a GIF, and then you can post it somewhere, or you can put it in a presentation. Yes, Copernicus Land Monitoring Services data. So the data sets we have here, Sentinel-1, I've shown that very briefly. Sentinel-1 mosaics, that's actually an interesting one. It's a monthly product of all the Sentinel-1 images using terrain flattening. So actually, if you're interested in working with Sentinel-1, this is a really nice product to start with, because it has the speckle removed through the multi-looking, because it's averaging across a month. And it's also just a smoother, more robust product to look at, because the terrain effects are also smoothed out. So this is actually a really nice tool. We create these mosaics for the sake of AI readiness. So if you have a machine learning or an AI tool, you want to have data which is noise-reduced, gap-free, in the same projection system, and then it's a lot easier to work with these mosaics than it is to work with individual images. And then we have Sentinel-2 mosaics. These are quarterly, so every 3 months you have a product, which is generated from the cloud-free pixels of those 3 months. And then we have Sentinel-3, so 300-meter resolution daily data, used a lot for meteorology and water quality, but also for more detailed vegetation investigations. Let me show you a quick spectral explorer. So you see that Sentinel-3 has 21 bands. So it gives you more information on the status of vegetation and on the properties of the land, and it also has a thermal sensor. Sentinel-5P is about air pollution. So this has pixels of 5 by 7 kilometers, And they are, in the current format, they are not oriented north-south, they are oriented along the track of the sensor. Here you have information on various atmospheric pollutants. So this is a sensor that you can use for air pollution analysis. It has gaps with clouds. We have the elevation model. This is, again, something you can use in queries, or you can use it for atmospheric corrections. And we have Copernicus Land Monitoring Services data. So this is actually a big collection of environmentally relevant biophysical variables. It used to be available previously in the data browser of the Copernicus Land Monitoring Service, and now recently it's been integrated into Copernicus Data Space Ecosystem. So what we have here is land cover maps. So this is a global 10-meter land cover data set from 2020. And we also have biophysical parameters. So soil moisture, snow, temperature, reflectance, vegetation properties like the fraction of absorbed photosynthetically active radiation. And we have water bodies extent and lake water quality. So if you're not really interested in satellite imagery, but you actually want the end product, then the CLMS data is actually a really, really good starting point. We will be looking into accessing CLMS data as well in the Jupyter lab. Okay. Any questions to Copernicus browser? Oh yeah, custom scripts. Let's see the exciting part. So coming back to the browser, let's just open a Sentinel-2 image, the usual way. Probably the same image from the 7th of September. And so I've showed you this button. This is where you actually access the code, which is part of the API request and doing the data processing for you. So if you click this little button, what you will see is 50 lines of code explaining what the server is actually doing with your data set. So these are the bands that are being loaded. This is the resampling. This is the process. And then these are some settings. And this is how the output is generated, which is actually used by the browser. Now, here in this course, we will not be dealing with OpenEO requests. We will be dealing with Sentinel Hub requests. So if you click the custom script and open up again this code window, you will see the process that is taking place for visualization. So let me show you once more. You go to a place, you load the data product. You select the visualization, and you click on this Show Custom Script option, and select Custom Script. And now if you open up this code window, you will see the exact code which is in the background generating your visualization. Okay, everybody reached this phase? Everybody has a custom script code open on their desktop? Okay, now the magic is starting, because you can actually edit this code. So if you change band 8 to band 7, you can run it again, and you will see something different, right? Or if you go back to band 8, and you set the min val to 0.05, you will be adjusting the stretching, you will see something different. So this code can be directly edited inside the browser, and that means that you can actually experiment with generating your own coding tools, and you will see the result immediately in Copernicus browser. You will see how it looks like. And now we have a big collection of custom scripts. So if you just go to customscripts.sentinelhub.com, this is a repository on GitHub, which holds about 100 different custom scripts for different applications. So this is our main repository for these scripts. Custom scripts with a dash .sentinel-hub.com. This is our custom scripts repository. It's an old thing, so this existed already before Copernicus Data Space Ecosystem in the days of Sentinel Hub.io browser. A lot of users contributed to this, and so that's why we have all these different codes. And now, let me show you how to use this repository. If you go to Sentinel 2, you will see a selection of different custom scripts for different applications. So this includes spectral indices, vegetation, RGB composites, even pretty scripts for art. You can choose several different ones, but I suggest we start with KNDVI. Has anybody here heard of KNDVI before? Okay, KNDVI is the next big thing after NDVI. Essentially what happens is you're applying a different transfer function. So NDVI creates a linear correlation between vegetation properties and the difference between the near-infrared and the red band. Now KNDVI, kernel NDVI, takes this transfer function, and instead of a linear transfer function, it applies something like a sigmoid transfer function, which means it stretches out the interesting part, where most of the vegetation is, and it avoids the over and under saturation. Let's go and check, right? So over here, if you go, you can also search like this, right? If you type KNDVI, it's taking you to kernel NDVI. You want Sentinel 2 KNDVI, and you can just copy over here. This is the full script. So it has a setup part where you are preparing the bands that the script is going to use. Here we are just defining a color ramp. And then it has this part, which is the evaluate pixel part. This is where the mathematics happen with the bands that you loaded in the beginning. And this is where the outputs are also generated. So you copy all this. You go back to Copernicus browser. Again, you will have to open the custom script. So if you're still with the visualization, you open the code, you select custom script, you open up the code window, you select it all, and you paste in this script which we just generated, or we just took from the repository. Come on in. Okay, so what you see here, first of all, it's got the cloud masking. So the clouds and the cloud shadows are handled, they are not on this green palette. Let's find an image which is less cloudy. Going back to the 7th of September. And so here, you see a stretch. You see a color ramp applied to the vegetation. How do we know if this is better or worse than NDVI? We can create a compare. So over here, you can click Add to Compare. And you will see here in your compare that you have one layer in your compare, right? We go back. You select NDVI. Add to. Add to compare. And now, if you click these two arrows, you have two different layers, one on top of the other. How did we end up here? Okay, it is just the preview is wrong, but otherwise it's okay. So if you pull this slider, you will see that one side of the image has NDVI, the other side has KNDVI. And especially in places like this, right? You can see that KNDVI enhances the subtle patterns of the vegetation slightly better. So this is how you apply a custom script. And we will be doing the same thing in an API request in Jupyter in a moment. But I wanted to show you the structure of how scripting works in the browser and how you can actually prototype your scripts in Copernicus browser. Any questions to Copernicus browser before we move on to Jupyter? Okay. How many of you have worked with Jupyter before? Great, okay, then we don't really need to do the introduction to Jupyter part too much. We are moving over to the Jupyter lab, and we have to generate our user account credentials. So in the data space, we want to go to Analysis on the main menu, Jupyter lab. And then here, access Jupyter lab. And this is where you get the virtual machine, right? So now we are spawning a small dedicated virtual machine for you on the actual infrastructure, which is also hosting the Sentinel data. You can choose between a small, a medium, and a large. It's all free. You have to prove that you are not a robot, and then you start. This takes a minute or two, depending on the occupancy of the server. I hope it's going to run fast this time. But in the meantime, there's something we can do. Has everybody reached this phase? Everybody has a server starting up? No? How can I help? Let's go through it once more. So it's dataspace.copernicus.eu, CDSE main page. You are already logged in with your user. And then here under Analysis, you click Jupyter Lab. And then you just click Access Jupyter Lab once more. It's a bit complicated, but we have to go to a different server to do it, so that's why we have these steps. Yes, in the meantime, the Jupyter Lab is set up for me. And so when you go to Access Jupyter Lab, it will prompt you for a small, a medium, or a large server. You select one, you click the CAPTCHA, and then you just wait for the server to load. Does everybody have the lab open now? Hands up everyone who is stuck. Great. So this is the entry point to coding Sentinel data on a virtual machine. What you see here is that you can do this in several languages, right? So typically we do this in Python-based Jupyter, but you can also use Julia. And some people like to use R, so that's also available. And actually, in the background, we are now working to make this available for MATLAB. So if somebody likes to work with MATLAB, and if they have a license, then you will also be able to access Sentinel data with MATLAB. Oh yes, and you also have Snap. So Snap, this big ESA software package for processing Sentinel data, is now also available in the Jupyter Lab. It's not completely cloud compatible. You have to create a subset of data and download it to your storage in Jupyter, but then you can run Snap on it. Okay? You get a small storage space, which is kept for you for a month. You get a notification when it's being deleted. If you are active in it, then it's sustained for more. So the month is calculated newly every time you do something in that folder. And then this is where we have our code samples. So you go to Samples, Sentinel Hub, and these are the notebooks that we will start working with. So our first notebook here is Big Data from Space 2025, Intro to Sentinel Hub APIs. Open that one. Has everybody reached this step? Or is something wrong? So it's inside Samples, Sentinel Hub, BiDS' 2025 Intro to Sentinel Hub APIs. So the way the Jupyter notebooks work, you have these text parts which are markdown, and then you have code which you can actually run inside the lab. And the output of this code can be visualized directly in the notebook. So this is how we will be looking at the results of our satellite imagery. First of all, we have to import some utilities. So we import matplotlib, pandas for handling the data, contextually. Do you know contextually? It's a library for handling maps inside a Jupyter notebook. So with contextually, you can create a map view, which you can then zoom and pan, and you can add various layers to it. It's actually quite powerful. We import getPass for handling the passwords, NumPy, Shapely for handling the geometries, and then from the Sentinel Hub Python package, we import all these functions. Because again, for advanced developers, there is a Sentinel Hub Python package out there which allows you to do all this inside your own local computing environment without the Jupyter Lab. Right? So we run this cell, Shift-Enter. And then while the cell is running, you see a little star, and then when it's done, you see a number. Now we handle our credentials. This is a bit of a complex stage, but once we have it done, it's super simple afterwards. So this is done in our user account. We have to create an OAuth client ID and a client secret, which we are going to add to the code, and then it creates a configuration which is used when we run our Jupyter notebooks. So let me show you how this goes. We have to go back to the Sentinel, to the CDSE main page. So once more, dataspace, .copernicus.eu. And then over here, under Analysis, we go to Sentinel Hub. And this is going to open up your Sentinel Hub user dashboard. And this is where you can create the credentials for the OAuth client. So dataspace.copernicus.eu, Analysis, Sentinel Hub. And then over here, at the bottom left, under User Settings, you will see these OAuth clients. If you haven't created one yet, then this is going to be empty. And then you click on the green button to create a new one. Give it a name. And you can also give it an expiry date. Normally, these are valid for 90 days. I'm setting mine to expire tomorrow, just to make sure that nobody is going to use it. OK? And now you click Create. So everybody got this stage? Good job. OK, this is what you see, right? And two ugly codes of numbers and letters. And what you want to do is to copy these in a safe place. So typically, I open a text file, I copy them in, and I store them somewhere to make sure they don't get lost. So with this little button here, you copy the ID. And again, you copy the client secret. And once you have this, you can close it. If you lose your credentials, no problem. You can just create a new one. And then you can use that again and again. OK, everybody confident about their Sentinel Hub credentials? Great. So now we go back to the notebook. This is the cell where we are setting up a configuration that's going to handle our credentials in the future. So we have to uncomment 2 lines in this cell. We have to delete the hash in front of config.sh client ID. And the other hash here, config.sh client secret. And finally, config.save CDSE. Right? Once more, this line, and this line. And now we are running the cell. And this is prompting me for my Sentinel Hub client ID, the ID I just generated on the other side. So am I copying this? And I'm also copying my client secret and pasting it in. OK, now the system knows who I am. Once you've done this, if you are running the notebook again and again, you can skip this cell, and you can just launch the configuration in the next cell. OK, now we are defining an area of interest. Again, we are working through API requests. So we are telling the computer what to do. We are telling the remote system what data to query, how to access it. So we have to provide some guidelines. The first thing is we define a bounding box based on the coordinates of Riga. We set the resolution. The highest resolution we can get with Sentinel-2 is 10 meters. We generate an object from this. And then we want to visualize this in contextually. So we create a data frame. We are reprojecting it. And then we are generating the visualization with a base map. And we are labeling the coordinates. Right? So all this big cell is just about showing where we are, creating a bounding box, and putting it on the mapping contextually. So we select this cell. We hit Shift-Enter. and we wait for a second for it to load, right? So this is our bounding box. You will see the background. If you want to run the whole thing later on for a different area, all you do is you change the coordinates of the bounding box, and you run the cell in the very same way. Okay? Now, we move on. We create a process API request. So process API is the Sentinel Hub tool, which is generating a raster output. This raster output could be the product of a complex calculation or NDVI or something similar, or it can just be a true color image. But the main thing is that the output is a raster. This is what process API does. Okay? So what we need for a Sentinel Hub process API request is the input data collections, the format of the output, the bounding box, the mosaicing order, if we are looking at the time frame of several images, and the eval script. The eval script is the same thing as the custom script which I showed you in the browser. So this little snippet of code which defines what we are actually doing with the data. So in this cell, first we define an eval script. This is just a very, very simple script for true color. Again, the eval script has two parts. The setup function, where we are generating the inputs and the outputs. So here, the input is going to be the 3 bands, band 2, 3, 4. And the output is just going to have 3 bands. It's going to be an image. And then in the evaluate pixel function, the final product of the evaluate pixel function is an RGB array. It's an array of 3 bands, or 4 if you also want transparency. And then the numbers in this array are going to be in the order of red, green, blue. So we are assigning band 4 to red, band 3 to green, band 2 to blue in the regular way. Right? This little variable, evalScript true color, means this piece of JavaScript code. And now we are creating the request. So request true color, this variable, is going to hold the following parameters. The eval script is going to be the eval script true color, which we just defined. The input data is coming from this collection, so Sentinel2 L2A from sh.dataspace.copernicus.eu. And we have a time interval now, from the 1st of June to the 30th of June. And then the response of this request will be output in the form of a PNG for this bounding box using this configuration, right? So this is what the actual API request is. When you are using Copernicus browser, this API request is generated on the fly for you by the system. But when you're doing this in Jupyter, you can do it one by one. Okay, we run this cell. Nothing happens, right? Because the only thing we did is we defined this variable. We defined what request true color means. And now we are going to run this request. So request true color dot get data. This is going to be the true color image, and we are going to print it and display it. So here it just tells us that the download is happening. The return is an image of 2,136 by 2,222 images with 3 bands. And now we are displaying it here in the notebook. So we are using Plotly for this, and we generate a small image with a label. Right? Again, we run this cell, Shift-Enter. It takes a moment to run, and this is our image, right? So now, in the Jupyter Notebook, we have created an image which directly displays the output of the API request we generated. Now, what's wrong with this image? It's cloudy. So what can we do about this? If we go back to the API request and uncomment this line here, it says mosaicing order least CC. So remember, we have queried a series of images from 1st of June to 30th of June. And this was the output. This was the last image in the period, because the default setting for this request is that it's showing the latest image. If we change the data filter to show the least cloudy image and run the request again, including again downloading the image and displaying it in the notebook, now this looks a lot better, right? Again, if you want to do this for your own area of interest or your own time of interest, the only thing you need to change is the bounding box here in this cell and the time of interest over here. Yes. You can also add a filter to only look at images with a certain cloud percentage. You will see, just in the next notebook with NDVI, we are going to do that as well. Okay? So now we want to do an NDVI map. What do we change here? We change the eval script, right? Instead of generating a 3-band composite of RGB, we are generating a 2-band spectral index, and we are applying a palette, a visualization to it, right? So our eval script is going to look different. In the setup function, we want the bands 4 and 8 and the data mask. And the output is going to be a 4-band output instead of a 3-band output. Data mask tells us where the data is valid. So it's 1 where the data is valid, it's 0 where the data is cloudy or missing or not available. And then a 4-band output has red, green, blue transparency. So if the 4th number is 1, then it's visible. If it's 0, then it's empty, transparent. And if it's somewhere in between, then it's going to be an opaque layer, which is going to be showing part of the layer behind it. So you can actually play with this opacity layer as well. Now, in the evaluate pixel function, we are saying that our value is NDVI. We are initiating the image values as 0. And here we are defining a palette with a very simple else-if query system, right? So if the value is lower than 1.1, then it's getting the image values 0, 0, 0, and so on. All these are different shades of green. And then, in the end, we are returning the image values, which is going to be an array of these 3 numbers plus the data mask, right? This is our eval script. And then this is the request again. So our NDVI request is taking the NDVI eval script. It's taking the input data again from sh.dataspace.copernicus.eu. We are taking summary imagery. We have a data filter for least cloud cover, and the output is going to be a PNG. So we run this cell again. And then again, we have a cell for actually doing the download with the request which we defined in the previous cell. The little star indicates that the code is running. We have, again, of course, the same output dimensions, but now it's not 3 bands, but 4. And now we are displaying the NDVI image. This is what we have, right? So again, this is the same as clicking NDVI in the browser, but now our image is a PNG. It's a file that we can use for other purposes. If you want a 32-bit TIFF, then you just set the output type here to TIFF instead of PNG. And in the eval script, you set the number format to 32-bit, and then you will get a data file that you can handle with your GIS. Yes, I think so. Let me quickly check. Okay, this is Budapest. This is where I come from. Yes, under analytical download, you can do PNGs as well. Back to the notebook. Now, before the coffee break, we are going to look into statistical API. Statistical API is different because the output of statistical API is not an image. It is an array of numbers. They are in a specific structure. They are assigned to specific dates. You can actually define which statistical outputs you want. So it's typically the mean and the standard deviation, or the minimum, the maximum, the mean of the data, but you can define quantiles, you can define various statistical variables, and then you get a table or a JSON which is going to output these numbers directly without individually opening up the files. And you can add these to a table, to a NumPy object, and you can visualize them directly as graph, right? We want the same thing. We are also going to apply an eval script in the statistical API, but we have some additional parameters to set, including the time interval and the statistical outputs, right? Here, what we want to do is we are going to check the NDVI timeline of different crops in a couple of fields in Latvia. So here in the sample Sentinel Hub folder, you have a GeoJSON for some fields here in Latvia. And this is what we are going to read, and then this will define the limits of our API request. So here, we load the object from the GeoJSON. We are converting the fields to web marketer just to align with our base map. We are going to create a figure for the 3 different crop types, defining colors. And then here's the legend for our little map. And we are setting the boundaries, and we are adding the base map in contextually. And then we are adding a legend. So this is how we create just a very, very simple map object here in the Jupyter notebook, which is showing us where these fields are and what they belong to. So if I run this cell, the output is going to be a map, right? So you see latitude, longitude, crop type, and individual fields, which we have checked. And the base map is OpenStreetMap. So this is how contextually works and how you can overlay a GeoJSON on this little base map. Is this part okay so far? Okay. And now we are going to create an NDVI time series for all these fields. Right? So this means we will have a loop for the individual fields and for the individual bands by date within the time frame. And then inside this loop which we have defined, we are going to run a statistical API request. These are the time intervals. These are the output data sets. What we want is the percentiles of the NDVI value, and this is all going to a data frame. Right? So we have run this cell. We have defined the functions that we want to use. And now we are actually doing the API request. So here, once more, we have an eval script. This is going to be a different eval script because the output is not an RGB image. It's just a one-band statistic that we want to use. So in the setup function, we are using band 4, band 8, and data mask. But the output is not going to be called default and use 3 bands. It's called NDVI, and it has 1 band. And the other one is called data mask. Again, it has 1 band. And so in the evaluate pixel function, I have to define the values for these 2 outputs, right? So the NDVI output is going to be generated from index, and here you see what index is. And the data mask output is going to be generated from the data mask. This is my new eval script. Again, Shift-Enter, we run this cell, so now this eval script is defined. And now we are doing the actual request. This is our time interval for a whole year. We are doing statistical API aggregation. The eval script is the one we defined above for NDVI. The aggregation interval is for 10 days. So our Sentinel Hub request is running in 10-day intervals, and it's generating the statisticals, the mean, the standard deviation of the NDVI value inside these 10-day bins. The spatial resolution, in this case, it's provided by degrees, so it's about 1,000th of a degree because of the map projection. Here's the input data. Again, it's coming from the Sentinel-2 L2A collection, and this is where you can define the maximum cloud cover, right? So inside the API request, if you just go max CC and then a number between 0 and 1, then that's going to be your cloud threshold. We are only looking at images which have a cloud cover below 20%. Now, this is not a pixel-wise cloud cover. This is taken from the metadata of the image. So it might happen that still some parts of the image are cloudy, but this is the filter that you can apply directly inside the request. And then inside the geometries, which we have defined in the cell above, we are running the statistical API request with these input data sets, this geometry, and this configuration, which is handling our credentials, right? And then we are rerunning this again and appending the request to the previously existing ones in the loop. Okay, this can be ignored. This is just a warning with the projections. And now we are actually downloading the the statistical data sets with this request. Okay, here you see we have used 184 milliseconds of CPU time, and we have successfully run this list of requests. Now, how do you generate an output from this? The direct output is just a JSON with a list of the data in the order according to the numbers. So you want to create a data frame, a pandas data frame, to actually look at the data. This is what this little helper function is about. Now you see something of the output. You have the time interval to and from for these 10-day intervals which we are investigating in. You have the minimum, the maximum, the mean, the standard deviation, and the sample count and the no data count. So again, depending on cloudiness, depending on the data mask, you might have more or less no data for a specific area. And each of these little requests has an ID. No, it's the same ID all the way. Then I guess it's probably the parcel ID. Okay, again, now this is matplotlib magic just to create a visualization, to create a time series graph from the data in the API. We are defining colors. We are creating a counter. We are storing the standard deviation because we want to put that also on the graphic. We have the IDs. And now we are generating a plot, including the standard deviation, and then we take the NDVI values from the pandas data frame, which we had above. We are creating a legend and then some formatting to show the output graphics. So this is what we get. So without actually downloading every individual image, querying 1 year of data, looking at only the NDVI, we could generate a pandas data frame, and we can visualize that as a graphic inside our little Jupyter notebook. So far, so good? Did it run for everybody? No error messages? OK. So you've seen these individual steps. We are able to configure an API request. We can handle the eval script. We can define the area of interest, and then we can set up the time series analysis. Any questions at this point? We have 15 minutes to coffee break. So 2,500 by 2,500 for individual requests. But you can run many requests. So let me show you the quotas in the documentation page. So this is what general users get. 10,000 requests per month. So depending on how many pixels Latvia is. We'll check this again. We actually have a calculator. We'll give this a test. Because this will also depend on how many bands, what you want to do with the process. So if it's just a direct access to the cloud-optimized GeoTIFF files, then that's 50,000 credits. There's a limit to requests per minute as well. So you have a bit of a speed limit as well. And then if you're using the other API, the OpenEO API, you also have 10,000 credits. So here under use cases, this is the PU calculator. This is actually not a standard service of Copernicus Dataspace, but some users have built this on top of the services we have. So if you just go over here, cdsc.github.io, cdsc PU calculator, then here you can move the map. We can actually go over to Latvia. You can generate an area of interest. Let's hope this works. Just a very, very, very simple bounding box. And now, depending on the mosaicing method, depending on the data set and the output resolution and the input bands, you will get a different number of processing units. Are you okay with 3 bands? 8-bit output? So this would be 5,000 PUs for one complete mosaic. So that means that in a month you can do 2 of them. Yes. Again, depending on your user type, some users are eligible for more. Let's go to the frequently asked questions. Which users are qualified for higher tier accounts? This is our most frequent question. So if you do a service related to producing Copernicus services, atmosphere, land, and so on, then you are immediately qualified for a higher tier account. Some partners from Copernicus participating states or international users also have this agreement, which means they are eligible. If you are a government agency providing a public service in an EU member state, then you can just fill out this user type request. It's going to be evaluated. You have to give an estimate of the use you want to do. So you have to describe in some words your use case and also the amount of processing units you are requesting. And then this is going to be evaluated. But theoretically, we're really trying to use this system as a way to support governance in the EU. So that means there's a high chance that you're qualified for more. If this is not the case, because you are a startup or a private company or something, then you can go through CrowdIAS. So CrowdIAS is one of the commercial virtual machine cloud providers inside CDSC. It means that it's the same physical infrastructure. It's also the same APIs. So any code that you build in free CDSC, Jupyter Lab, or whatever, is also going to run on CrowdIAS directly because it has the Sentinel Hub APIs, the OpenEO APIs, the collection number IDs are the same. So that it's definitely, it's created in a way to smooth this transition period. It gives you a free trial, but there is also a credits for value creators program. Here we go. So this is again an application form where you can apply for some additional CrowdIAS credits. If you are a scientist or if you are a startup company or a service provider, then through this way you can, for example, you can get the Sentinel Hub Enterprise account or you can get a virtual machine. This is again not an automatic system, it's evaluated, but actually so far we don't have so many applications, so it's relatively easy to go through. And then we have the network of resources. So this is the funding scheme by ESA, where what you get is not actually money, but access to data. It can be commercial data, it can be data inside CDSC. So this is also a way to get an additional quota. They have a very, very friendly two-step evaluation process. So you submit an application, they give you a review, and then after that you can resubmit. So actually, a lot of my colleagues or NGOs I know have applied for Network of Resources funding and they have got their request. And there's an additional way. Yes. So on our website, we have some use cases, documents describing what people have done with CDSC. And if you submit such a use case, and it is actually published, then you immediately get 5,000 euros worth of extra credit. So that's, again, a way to get started. If you have an application, but you're running into the boundaries of CDSC and you just want to grow it, let us know how it went, describe what you are doing, and then you can get some extra credit. So these are some ways to grow your quota. And of course, we are pushing ESA to get more quota, so to raise the public quota for everyone, but they are paying for it, so this is always a negotiation, but this is what we have so far.
Basically, the suggestion is if you're running out of credits, first contact you and describe like who you are and like what's your use case, so there is possibility to
Yes, if it's a market thing, then you go to CrowdDS and pay for it. And for some users, that's the easiest because they are using a virtual machine service anyway, or for whatever reason. I think the prices are quite okay. But
Previously there were more DIS platforms.
yes.
And now BiDS is the one survived. Or
Yes. Well, Wekao has also survived, and CodeDE still exists as well. But the history of this is when ESA created the DIASes, they were designing these as public-private partnerships. So they thought they are funding the launch, and then they are expecting commercial entities to pay for using it, and that should keep the DIASes alive. And this hasn't really happened. So somehow the shift to DIAS-based processing in the market was slower, and so some of these DIASes died a slow and painful death. And essentially, CrowdDS is the one that's existing in this form. Wekao was sort of taken over by the EEA. And also some regions have their own sort of Sentinel mirror sites. So we have a hub in the Philippines. We have a hub in Latin America, which works as a DIAS. We also have Dunya, which is a processing platform for Africa. So we have something similar, but these are less of a sort of market-oriented things. These are more public things funded by Copernicus. But we still hope that people sort of grow services that in the end turn into something commercial and run in CrowdDS. For smaller services or for government things, the quota should be enough. But when you are really, really trying to grow across scale, sooner or later you are probably going to end up on CrowdDS or OTC or one of the other cloud providers.
For scientific purposes also, it's necessary to pay.
Well, if you are using it at that scale, so if you are going beyond the free quota, and if you are not recognized as a Copernicus service user, then for virtual machine processing you have to pay, yes. But CrowdDS actually has a discount for scientific users, something like 18%. So it's possible to negotiate with them. And the CrowdDS Credits for Value Creators program also applies for science. So you should be able to ask for a first initial credit. But scientific users, they typically tend to go with a public quota. Of course, the trick you can do is once you are creating something across a large area or you are serving external users, you want to convince them to register to CDSE themselves, and then they are consuming their own quota instead of your quota. So if, for example, you are providing data for a farm management system, you can do it through your quota to a certain extent, but if the farmer registers, then for their area of interest, the free quota is going to be absolutely enough, even if it's a large farming company or whatever. So by providing public data through an individual registration basis, it's really possible to serve many, many users. More questions? Yes?
You mentioned the Sentinel one mosaic. Is there a description about it?
Oh, yes. I wrote it. Let me try and search it. Under the news section of the CDSE page, we have short announcements, but we also have sort of longer blog posts or descriptions of new data sets. Let me try and search. Yes, this is the one. So, announcing Sentinel 1 monthly Mosaics Copernicus data space ecosystem. And here's some individual time lapses. Here's a description of the problem of working with Sentinel-1 data. I mean, Sentinel-1 doesn't have true color, so it's not so easy to get started. And then we describe how the data is built. So this sort of terrain flattening algorithm, which equalizes the effect of the side look angle based on the terrain. And then we have a short comparison between regular Sentinel-1 and the mosaics. and an interpretation guide to the individual bands, and a comparison of different visualizations. So this is actually quite an extensive guide, I think, to Sentinel-1 mosaics. We also have the same for Sentinel-2 mosaics. We have a guide to Copernicus land monitoring service data. This is a long read because there's 15 different data layers, but this describes the data products you get with from the Copernicus land service data sets. Some of these examples or blog posts also come with code snippets, which you can use directly. And then we have the use cases section, which is a bit less technical. This is really about individual applications from users. And then we have the documentation, which is quite extensive. I mean, it includes all the different API tools, all the different data sets. And finally, we have the forum. So obviously, this is the best place for asking questions. We have quite an active forum. We are starting to have users answering each other, not just the support team, which is a good sign. And if you post a question here, then it's also viewed by ESA. So one of our performance indicators is how fast we answer our forum posts. If there is something that users repeatedly ask for, then ESA is pushing us to implement it or to correct it. So this is how any bugs or problems or also feature requests can be handled. We also have a QGIS plugin. Because the nice thing with Sentinel Hub APIs is that you can also create an OGC-compatible output. So if you are doing an API request, you can release the result as a WMS or WMTS, and that can be picked up by a WebGIS or by desktop GIS software. Let me show you very quickly how that works. You go back to the dashboard. Here you have a configuration utility. And so a configuration is a collection, a subset of the data on the server with a predefined set of layers or eval scripts. And then so here I'm creating a new configuration. I'm basing it on an existing template. Let me see, simple Sentinel to L2A template. This is my configuration. So here I have individual layers. And every layer has its own eval script. Again, this is something I can edit by hand, or I can add new layers with a different custom script. And then if I want to serve this as a WMS, all I do is I go here. I select WMS. And then here I am getting a URL, which I can directly forward to my GIS software. And the Copernicus Dataspace Ecosystem Sentinel Hub QGIS plugin does that automatically. So if you just take it from the plugin repo, then and then you log in with your OAuth client ID and client secret, then it's going to access your configurations. You can select them, and you can load them directly into QGIS and work with them. One more little gadget before the coffee break. This is the Request Builder. Request Builder is a graphical interface to coding API requests. Again, this is to make things easier. So it takes all the parameters of an API request, and it allows you to set them up by hand. So again, an API request has an area of interest, which you can draw on this little map here. And then it will, actually we could recreate this. So if I am Moving to a different place. Let's go to Riga. See, then here's my area of interest in code. I can select my data collection, my time interval, my output. Here I can select the image format. And then here I can add the eval script. It works in the same way as the browser. You can just copy and paste it. And then your request is going to be built here. So this is the actual code of the request. And you can copy this and paste it into your own Python code or your own Jupyter notebook. Or you can just send it and run it directly. And then you're going to get the output image in your downloads folder. So this is, again, a good way to troubleshoot, a good way to hack requests or to understand the components of an individual request. If something is not working in your code, you can try building it here and running it over there. So this is a handy little tool for creating your requests. More questions? OK, thank you for following on so far. We've got coffee break until, I think it's until 11 o'clock. Yes, we start at 11. Thank you. Welcome back. We have 2 more notebooks to go, and then we can also explore some of the other examples if we have time. Once more, we will look at a statistical API request, and then we will look at time series and explore Copernicus land monitoring services data. But before I dive back in, I want to ask if anybody has questions. Sometimes you realize you have a question after the coffee break. Great. Okay, so we move to the next notebook, which is the Introduction to Statistical API. Just click that, open it. Don't forget your credentials. Again, we import the libraries, the dependencies, and then we handle our credentials. Theoretically, in the previous session, everybody has created a configuration. If you also uncommented this config save line, then you don't have to re-enter your credentials. You just run this next cell, and that should connect the previously defined configuration, and we will be able to work with it. I hope so, at least. If something goes wrong, we will have to go back and re-enter our credentials, but this should work just with the configuration. Okay, so once more, we use the fields from this GeoJSON, which we have in the folder here. We define our colors, we define our legend, we visualize them on contextually. Yes, here we are. Here's our crop types. Again, we will see the growth cycle for them. And based on these growth cycles, you should be able to separate them using simple thresholds or a machine learning pipeline based on the output of the statistics API request. So we've seen similar examples for cap monitoring. What some countries do is for every field, they create a statistical API request. You get a time series. And then instead of pushing the images to a machine learning model, where you would be working with millions of pixels, you only push the fields and the time series of the fields. And then on that table, the model can learn much faster because it's smaller, it's compressed data, and you still get the crop classes, the crop outputs. Okay, again, here's the helper functions, just to put all the data in a nice and clean table. And then here's the eval script for NDVI. So you all know this by heart now, that an eval script has 2 main parts, a setup function and an evaluate pixel function. And these 2, of course, they have to match. So in the setup function, we define the bands we used, band 4, band 8 data mask. In the output, we define one output called NDVI and another called data mask. And then in the evaluate pixel part of the function, we assign values to these individual outputs, and that's what our API request is going to use. So again, we have to run this cell where we define the variable called eval script. It's in triple quotes because this is a small piece of JavaScript code inside the Jupyter notebook, because that's what the API uses to handle these things. Some people don't like this because they want eval scripts in Python. We are not yet so far. We think JavaScript is a bit easier to handle, but this might be a direction of development for the future. Okay, so now we build the request. We read the file for the fields. We create a geometry object from it. And this is going to be a Sentinel Hub statistical API request with an aggregation interval of 5 days, a spatial resolution of 1/10,000th of a degree, so approximately 10 meters, and a time frame of 2023, January the 1st to December the 31st. And our eval script is going to be the eval script which we defined in the previous cell. The input data is coming from the Sentinel-2 L2A collection. The configuration handling our credentials is the one we defined at the start of the notebook. And then we can actually run this request. Okay? If we uncomment this little hash here, response 1, then I think this is what the output looks like, right? So this is the native output of Sentinel Hub Statistical API. It's a big, ugly JSON. Of course, it's in an ordered form, so it's possible to read these data points in using various helper functions. Actually, it's quite long, since this is a year of data. But this is what it looks like. This is the native output of statistics API request. So now we want to put this into a data frame. And so this is how we, using this very simple helper function, we define the columns and the rows, and the data points are inside the individual cells. Instead of the standard outputs of min, max, mean, and standard deviation, it's also possible to define various different statistics, quartiles, medians, other bounds, so I don't know, 95 and 5th percentile bounds. This is all available inside the statistical API documentation. So now we integrate the data into matplotlib, and we have a time series. What's wrong with the time series? Of course, it's cloudy, it's noisy. Come on in. So if we change the request, if we add a filter for cloud cover, then we are going to get a much cleaner time series. We don't change the eval script. There's only one thing we change. It's a data filter, where we say max cloud coverage is 10%. Right, so here's our API request, which is the same. The geometry is the same, the fields are the same, the aggregation is the same. We just add another argument. Data filter is max cloud coverage 10. It's the same as what we did in the other notebook with max CC 0.2, just in a bit more human-readable format. So if I run this cell again, now we have a different request which is filtered. We read the data into the data frame again, and now we can visualize it, and it's going to look completely different, right? So this is what we started with, and this is what we got. Of course, filtering everything down to 10% cloud cover is not always available. Sometimes you don't have sufficient images if you want to keep it below 10% cloud cover, but this really shows how smooth the time series can be if you filter the cloudy pixels away. You can actually try and change up here the maximum cloud coverage to a different value. Let's give this 30% and run it again. So now it's slightly more noisy, but you also have more data points. And now we are generating a statistics API request which has several outputs. So previously we only had NDVI and data mask. And data mask was not a real output, it just defined when we have an output and when we don't. But if you create an eval script which has several output variables, you can pass all of that to the same statistics API request. And that means that in one single API request, in one run of the query, you can create many, many different outputs. So it's actually super efficient also for processing units, because you're not using the same band twice, or you're not creating separate requests for the different outputs. So right now, we have NDVI and NDWI, so the water index. So we are loading 3 different bands and the data mask. And in the evaluate pixel function, we are defining these 3 different outputs. So when I say index, and I give it an array of 2 bands, it's just creating the classical subtraction divided by addition index, which, for example, NDVI or NDWI is composed of. So we can also define it in this very, very simple way. Right, so here's my eval script, which actually creates multiple outputs. And now I have a statistics API request again. So I take the geometry values, I take the 5-day aggregation interval, my resolution is the same. I'm going from the 1st of May, no, the 5th of January, no, the 1st of May to the 30th of April. No, that doesn't make sense either. Okay, it's 2 different years. It starts with 2022 and goes until 2023. So that's how the time series is put together. I have a cloud coverage filter for 10% again. And then I can run the request. So again, it takes some time because it's querying several different bands. It's a time interval that's slightly over a year. But now I'm building the pandas data frame, which now has min and max values for NDVI and NDWI respectively in the same data frame. So again, you could, for example, generate a product of these two inside the data frame based on your API request. And now we visualize it. So here is our time series of 2 different spectral indices at the same time. Any questions to this notebook? All clear? Is anybody ready to? Okay, let's actually try this. Let's switch to, yes, please.
When you are talking about the financial issues, does the software tools are freely available, or we need to pay for the data, or also the software tools is needed to pay?
This Jupyter lab and these data sets are completely free. So the code in here, the tools we are using, the Sentinel Hub API, is absolutely open and free. Also, the browser is free. We have a quota, so you can't use an infinite amount of data, but it is freely available within that quota to anybody. So if you want to change from NDVI to KNDVI, how do you go about that? Which part do we change in the request? We change the eval script, right? How do we change it? We go to the repository. Sentinel 2 KNDVI. Actually, we have code here for the raw values. So we can open that up. It takes band 4 and band 8. So here, we are also taking band 4 and band 8, right? That's easy. Which line is the actual index? It's this one, right? So it's the tangents hyperbolicus of the square of the NDVI, essentially. So if I take this, I copy it over here. I add a new variable. I also have to change it in the setup function, right? Because here I had an output called NDVI. Now I'm calling it KNDVI. So I've redefined the eval script. Actually, I can give it a different name. Eval script K. And then in the request body, I'm changing the eval script to eval script K. I'm checking whether the NDVI variable is anywhere here, but I think it isn't. No, something is wrong here. Okay. Yes, because this uses samples instead of samples. So here we have sample. Over here we have samples. If anybody more proficient with Jupyter notebooks actually sees the error, then go ahead and tell me. It could be related to the brackets. Okay, now this looks successful. Yes. Here we have the K and DVI values inside the data frame. So there was a bit of syntax cleanup to do. Oh yes, this is because we don't have an NDVI mean and an NDVI standard dev. We have a K NDVI mean and a K NDVI standard dev. Has anybody got this on their computer already successfully? Yes? Good. Did you go through all this, or did you just keep the variable name? Okay. Here we are. Okay, I still need to change the label back, but otherwise. The standard deviation is coming from the wrong place. Mm-hmm. Yes, I need another K here. Yes, now it looks good. Okay, so this is how it works. You take, it's like Lego. You have the building blocks here in the Jupyter notebook. You can change the area of interest. You can change the spectral index. You can change the time frame. But all in all, the statistical API is a really, really fast tool to work through hundreds of images and get a result that you can work with. Let's see how this goes with longer time series for multi-temporal analysis. And we are scaling up now to go across the whole area of Latvia. So the next notebook, BiDS'25, multi-temporal analysis, CLMS data. Open that one, please. Again, we are importing the same dependencies. There's one thing I want to show here. There's this utils. Utils is a small piece of Python code that handles the import of matplotlib, numpy, and handles the plot image function. So these notebooks will only work if you have the utils.py in the same folder. If you create a copy of it in your own folder to manipulate it, you have to take the utils.py with you. Okay? Successful setup. Again, we already have the configuration, so we only have to run this third cell. And now, we take the boundaries of Latvia. Again, here we have a data folder. This includes a couple of countries and a couple of area outlines for different notebooks, not just this one, but other ones as well. So we are loading the geometry of the Latvia boundary from Natural Earth. Actually, Natural Earth is a really nice source of these free online country boundaries and various other basic background data sets that you can use. We are reprojecting it. We are keeping it in degrees for compatibility. And then we are visualizing it in contextually. Okay? We have a slight warning because of the reprojection. This is our map of Latvia. So you see that the boundary is not as complex as the one that you see on the map. It's a simplified version, but it's sufficient just for our purposes now. Right? And now we are looking at net primary productivity from CLMS. Let's go back quickly to the browser and take a look at this, just so that you see what it's about, right? Browser, browser.dataspace.copernicus.eu. We zoom in on Latvia. And then under data collections, we go to Copernicus Land Monitoring Service, biogeophysical parameters, vegetation, and then this is net gross primary production, 10 daily NPP. RT 0, 1, 2, and 6 are different processing levels. So we are integrating data across different time frames and different reprocessing levels to create this data set. We can go with RT2 for now. And then you go to show latest date, and you see a map. Okay, this was a bit complicated. Let's go from the start again, right? So this is what you normally have, right? Sentinel-2. Copernicus Land Monitoring Services down here. And then CLMS has two big data groups, land cover and biogeophysical variables. So it's all in a nested tree structure. You go to biogeophysical parameters, and then you will see soil moisture, snow, temperature, vegetation, water bodies. And these are all fun to explore. Take a look at these data sets in your own time. But vegetation, again, we have 6 different vegetation properties, burnt area. These are related to this is FAPAR and leaf area index and foliage cover. This is various ways of calculating NDVI. This is phenology, actually, so how long the growing season is and stuff like that. This is dry matter productivity, and this is net and gross primary production, which people use for calculating biomass and productivity and various carbon indices. Right, so this is how you pull it up in the browser. But this is a data collection just like the Sentinel satellite collections, which is also available for Sentinel Hub in the Jupyter lab. So we can access it using the collection ID, and we can create API requests which work with it. Did everybody successfully open it in the browser? Yes, please?
You told that you have country boundaries. Do you have also the economic zone of countries in the sea, for example?
Let me check. Because here we have the country boundaries just for visualization purposes. No, these are only on land. But the data set I was suggesting here in the notebook, this is from the Natural Earth countries data set, so it's just an online repository of free data. I think that would probably have the economic zones as well. But right now the country boundary runs along the land boundary. I guess it should be available. If not, it's probably possible to generate with a buffer operation, actually. Okay, so here we are looking at the net primary productivity layer. So we have to have an eval script which accesses this data set. That's the input. And then we have various different outputs here which I have to explain. This is the default output which Copernicus browser uses for visualization, 4 bands red, green, blue transparency. This is the index, which it uses for generating the histogram. Remember in the first session we saw how to take an area of interest and generate a histogram of the data set. This is the EO browser stats, which it uses to generate the time series. And then finally, this is the data mask. Right? The visualization and the analysis eval script here, it takes the original value from the NPP band. It adds a factor and an offset, which you can adjust up here. And then it applies a palette, and it visualizes it. And again, in the return part of the evaluate pixel function, you see that the visualization is coming from the image-vals palette, and the index and the EO browser stats are the actual values of the band. So here we define this eval script, NPP eval script, in this cell. Again, this runs fast because it's not moving any data, it's just defining a variable. But this is the eval script that we are going to use for the statistics API request in the next step. Right? Now, we are generating a statistics API request for the area of Latvia and net primary productivity. So we take the geometry, which we have already defined here. Again, we are taking the data from the net primary productivity band. And here, you actually use a bring your own cog collection ID. because not every data collection inside Sentinel Hub has just simply a name and a label, because we have too many of them. But in the documentation, if you go to Sentinel Hub and data, CLMS, biogeophysical parameters, vegetation, net gross primary productivity, you should be able to see the, yes, here's the BIOC collection ID. So this is where you find the collection ID if you want to use a data set which is within CLMS inside an API request. Okay, so here's the ID. BIOC, BYOC stands for Bring Your Own COG. A COG is a cloud-optimized geotiff. And this is because Sentinel Hub enables you to load your own data set into the repository and use it with the same APIs as a Bring Your Own COG data set. And this is actually how we ingested the CLMS data. So that's why it has these complex IDs. But this means that you can generate another custom data set and access it in the very same way. And if we have a bit of time in the end, I can show you how. Okay? So now we have set up a request. Actually, this is a process API request, right? This is not a statistics API request. Okay, and now we visualize it. We create an image out of it. So we take the PNG. We run the API request, and we put it into matplotlib. Right? It's slightly stretched because of the map projection, but this is the mosaic of net primary productivity using CLMS data for Latvia. Okay, is the part with the BIOC IDs clear? Okay. So now we want to look at this in a time series. So we give this a start and an end time. We run it for a series of time slots. So these are the monthly time windows. And then we are rerunning the requests using this eval script and this BIOC collection. And what we should get is a set of images from the mosaic. Here we have a slight bug. Let me see clip. No, this is even worse. My colleague William told me this should work if I add these extra parameters, but apparently that's not the case. So I won't be able to give you this mosaic unless somebody knows what to do. Yes? No? This should be a clip based on values. Oh, yes. Thanks. OK, so if you add amin equals 0, amax equals none, then you get this plot of the time series. So you see the images for the individual months, and you can see how the net primary productivity grows throughout the year. I'm showing the code once more. We're talking about this line, right? So to np clip, you have to add A min equals 0 and A max equals none.
But you can just simply just take out the clip function.
Ah, okay. That works as well.
Yeah, you just leave image inside.
Like this.
Yep. It will produce the same.
Cleaning up the brackets.
At least for bigger.
Yes, it works as well. So how would you go about doing this for a different variable? Instead of MPP, GPP or something? You have to go back to the documentation to find the data type identifier. GPP data type identifier. You change this in the request. The data collection ID over here, and then it will run for a different parameter. But let's move on to forests, right? Now, we want to take the forest type map, which is over here in the land cover data. So back to Copernicus Land Monitoring Service, land cover and land use mapping, dynamic land cover. Nope, it's the other one. Yes, forest type. So if you go to Copernicus Land Monitoring Service, land cover and land use, LCC 100 meter yearly V3. This has two layers, land cover classification and a forest type layer. It has more because every layer has its own probability in there and you can do fuzzy mapping and stuff if you want, but it has a forest type map. And you can access this forest type map again inside an API request. So here's our eval script. Again, we have a factor, we have an offset, but these are 0 and 1 at the moment. We are taking the forest type band from the input layer. And we have 4 outputs. The default one is going to be the RGB visualization based on the palette, assigning a color for every class. The index is going to be the number, which refers to the class. The EO browser stats is going to be, again, the number and I guess the mask, and then the data mask. So what we do is we take forest type, we add the factor and offset, but this is 0 and 1 in this case. We make a small check if the data mask is 1, then we use the data with the get color palette. If not, then it's just not a number and it's empty. And then here we have a color map for the individual forest type values. So each one of them has a different color, a different RGB color. And this is what the evaluate pixel function uses to generate the palette. Right? So now we're working with discrete values, which we assign to a palette instead of continuous values of a specific quantity. But again, we define this eval script as a variable. So we run the cell. And then, again, we are querying this data set inside the area of Latvia. So we are running the Sentinel Hub request with this eval script for this particular bring your own cog collection. And we are using one single date, so January the 1st, 2019, and we are outputting a PNG. So run the cell. We get the little message that this has worked. And now we want to visualize this. So this is about first running the request. Yes, it's of list class and it has a length of 1. It has a small number of pixels since this is lower resolution data. And now we have defined the legend. We have defined the plot from this PNG. And we are creating an image in matplotlib. See, this is the forest cover map. Again, we have coordinate legends, we have or coordinate longitude and latitude, we have a label, and we have the palette for the individual forest types. It's stretched because of the projection. And now, if we want to do statistics, we want to check the proportion of individual forest types within Latvia, again, inside an API request. We have to change the eval script because now we're not visualizing it with a palette. We are actually taking the individual numeric values of the classes from the raster data. So we have a stat eval script. Again, it's setting up the output. We have two bands, forest type and data mask. And then the forest type band is going to have this data ID and one single band. And so we have defined the eval script, and now we create a statistical API request. So we take the geometry from the Latvia GDF file. We are aggregating in a one-day interval, but our time interval is one single day, right? Because this is a map that's generated annually, once a year. We are taking the input data from this bring your own cog collection, so the forest type map. And then we take the calculations from this part above. So this is where we are creating 7 bins for the histogram, and we are running the request, right? So our output is going to be this little JSON here. Again, a histogram of 7 different bins. Individual counts we have here. These are the different forest type classes and the overflow and underflow. And now we are extracting this into a histogram object. We are converting it to a data frame, right? So for the class 0, we have 41,000 data points. For class 1, we have 11,000 data points. For classes 2 and 3, we have 0. And for class 4, we have 20,000. And 5, we have 19,000. And so now we are renaming the data frame, assigning the names of the individual classes to the categories we have in this little dictionary object. Right, so now this is a table that you can already start working with. And we are cleaning the data frame a bit, and we are plotting it in a pie chart, right? So in Matplotlib, this is called wedges. We are giving it some labels. We are defining the font size, and we are defining it as a circle, right? So this is the pie chart. Again, from this CLMS dataset, we didn't download it. We took it straight from the API request, and now we can look at the proportion of the individual forest classes. Everybody followed until here? Ready to take on the challenge? The challenge is to look at Lithuania and Estonia. So you would have to take the geometry from the Natural Earth dataset. It should be available as a shapefile. You have to convert it. No, it works directly from the shapefile. You would have to add it to your data folder. And then you can run the very same request, just changing the background geometry. And you should end up with a similar plot. What do you think? Ready to tackle that? Let's give this some time, right? This one. Because it's in the same shapefile.
Yeah, it's in the same shape. It's one big shapefile that consists of all the world countries. That's why. You had to know the data.
Yeah, the label is the same, but the area has now shifted to Estonia, already here in the context.li map. I don't even have to run this cell because the eval script is the same. But I have to rerun this because the geometry has changed. I have to rerun this as well. Yes, this is now Estonia, it's not Latvia. Nice. Very, very easy. Yes, I haven't changed anything, just the geometry in the background, so all the labels are staying the same, which is a bad job, but this is how we can very, very quickly and dirtily do this. Okay, I'm ready for questions. We have 15 more minutes. If nobody has questions, there's one more notebook I want to show. No questions? Okay, here we go. There's one called soil erosion risk down here. So in this one, we are going to create a really, really complex eval script, taking data from multiple sources. And we are going to compare elevation data with vegetation cover from Sentinel imagery, okay? Soil erosion risk. So I don't know how familiar you are with the universal soil loss equation. It's a model of the risk of soil erosion. It takes multiple parameters into account, obviously rainfall, soil type, slope, and vegetation cover. I think that's all. We can't model all of these, but we can model slope and vegetation cover directly from Sentinel data. And so we can create a very, very rough estimation of erosion risk based on these two parameters. But for vegetation cover, you have to look through a time series of images to see how frequent the vegetation cover was in the area. Okay, importing dependencies. Launching the configuration. I hope this is going to work here as well. Defining a bounding box. This little box here in the eastern corner of the image is a place in southwestern Hungary where we have a sort of a clayey, loose soil and some slopes. So it's really heavily affected by erosion. We get a lot of problems of erosion in this area. So this is our bounding box. We just add it as a parameter. Our time interval is April to September 2023. So essentially the agricultural crop growth period for the area. Also the period where we get the heaviest rainstorms. And now here's a magic eval script. What we want to do is to count the number of bare soil days over a time interval. So for this, we have to use a spectral index which actually looks at bare soil. So it separates bare soil from vegetated areas. We have to do some filtering based on clouds using the cloudy pixel mask which is already in the data. And then we have to count this number to find the proportion between bare and non-bare pixels. So how does this work? The setup function is going to be familiar. We take these bands. SCL is the scene classification layer. So this is the actual layer which describes when we have clouds and when we don't. Yep? Yes, we could use that as well. But that's probably not going to be as accurate as it would be if we would be looking into vegetation cover. But that would be a very straightforward way to do it, actually. That's not how we did. I'm showing you the scene classification layer here. So this is what you get. These are high clouds. Right? And then here's a little for loop. We are checking whether it's cloud. We are checking whether it's bare. And then we are either increasing the number of bare or non-bare dates by 1. And so the output of this level script is the number of bare and the number of non-bare and the number of cloudy pixels for a time interval. Right? It's easy. We just run the cell to define this as the eval script. And then we are running a process API request, which creates a TIFF output. And it's giving us the number of bare and non-bare pixels. And now the bare soil is among this array, the 0th one. So the first in the output from bare, non-bare, and cloudy. And then here, we are calculating the ratio of bare soil dates to the total dates in the time interval. And so this image is going to be yellow where we have a lot of bare soil, and it's going to be blue where we have vegetation cover or where we have many clouds. Right? This is going to be one input parameter for our analysis. The other one is terrain slope. For terrain slope, we had to create a custom collection because the terrain elevation is available. We have the 30-meter Copernicus DEM in the collection, but we applied a small GDAL function here to calculate the slope. We did this, calculated it on CryoDS. It actually took 1 day on one processor core to do this over the whole Earth. We didn't even multi-thread it. And then we made this available as a bring your own cog collection. Right? So for this, we have a slope, which is the output parameter. We define the eval script. And then here we have a process API request, which is again outputting a TIFF, which represents the slope. Okay? And now we've just very quickly visualize it. So this is giving me a slope map. Flat or horizontal areas are dark blue. Slopey areas are yellow. So you see that this does have quite complex terrain, this area. We have some of these valleys. And of course, the places where these are overlapping with agricultural fields, where we have a lot of bare soil, that's where we are getting the erosion. Right? And so, I mean, we don't have the universal soil loss equation here, but we have a parameter to change the relative weight of bare soil and slope, depending on which we think is more important. Right now, we are just weighing them 1 and 1. And we are calculating the minimum and the maximum of the relative erosion risk within this map, right? So here, this is where we actually calculate the relative erosion risk based on the data. And then again, we define a color map with white for the places where it's absolutely 0, and from green going to red with the erosion risk. And this is our map, right? So wherever we have forest or we have flat places, it's going to be 0. And in the other places, it runs from green to red. So what we did here is we combined an eval script that runs on a satellite imagery time series and counts the number of bare soil days, and a custom collection that we created processing the slope data and putting it back as a bring your own cog. And this is actually, it's all possible to integrate this into one single eval script. Actually, yeah, we can compare it with a true color image. Just to look at the cloudless mosaic. Again, it's going to be a process API request. And now we have a plot. So here you see the output of the Sentinel to cloudless mosaic and the soil erosion risk side by side. So this field, this is the most risky place. And the last thing I want to show is that this is a data fusion eval script which takes two different data sources. One is Sentinel-2, the other one is slope. And then this whole process, including the weight of the bare soil and the weight of the slope, is input into one single eval script. So it's possible to create an eval script which takes data from two different data sources. It calculates this time series analysis thing, counting the number of bare soil days. And finally, it adds the slope and it calculates the erosion risk. So this is I think, one of the more complex sort of pre-operational notebooks that we have. We have many more. We also have some for Sentinel-1 data. We have a notebook that combines accessing data from the ERA 5 climate data store and Sentinel imagery. So this is actually quite a lot to go through. But I think it's a really nice starting point for you if you want to work with Jupyter notebooks. 5 more minutes for questions. Come on.
For the land topography, do you use data from other maps? Or do you have from Sentinel the topography of the land?
I will show you in a moment. So the topography data we take from the Copernicus 30-meter elevation model and the Copernicus 90-meter elevation model. Here is some information. So this is from the World DEM. This is the standard data product of Copernicus, which is created from the TandemX mission. So it's a radar elevation model, which also means that the forests cause some errors. They are not perfectly removed. And in some places, it's gap filled with other data sets. But this is not a compiled collection of the national LiDAR or elevation models. This is one global data set which is created from satellite mapping. Okay, there's one final thing I want to show you, or two actually, events. So on our page, we have a list of events, and some of these are webinars. So we regularly have webinars on CDSC where we show various technical things or various use cases. These can be followed online. You can sign up and register. And we also have a YouTube channel. So here we have a collection of sort of the webinars, of course, that we show, some short videos related to the image gallery, but also more technical videos on how to use various aspects of the data space. We have also some very simple introductory ones. So this is probably a place to follow if you like learning from video tutorials online. And of course, we have LinkedIn. What else? That's the only social media we have. So come and follow us, and I hope to meet you again at the conference. We can talk about individual applications as well. Thank you for joining me today.